Chapter 11, Part 2, Synthesis and Reactions of Alcohols. So Chapter 11 is usually a chapter that most Organic 1 students embrace wholeheartedly because there's quite a lot of review material in this. There are a few new reactions within this chapter, but most of it is information that you've already learned. We're just combining it again and looking at it as only alcohol chemistry, whereas previously you saw a lot of these reactions as like part of an alkene chapter. So now we're just focusing on the alcohols. So a reminder, the acid catalyzed hydration of alkenes is one way to make an alcohol. You have to be careful with this. Remember that this is going to be Markovnikov addition and that rearrangements are possible. And our product here would be the more substituted alcohol. Now our next one is oxymercuration demercuration. This one is also Markovnikov, but it has the fun caveat of no rearrangements are possible because it doesn't go through a carbocation intermediate. This is not the best example because you're just going to end up getting the same thing as you did when we did this reaction a second ago in acid catalyzed hydration. But if we did have a situation where this had rearranged, this would not. Our last one is hydroboration oxidation. This is our anti-Markovnikov option. So this is going to give us the least substituted alcohol. So our product is 1-propanol. Now we've also seen most of these reactions, we've seen alcohols act as bases, like when we use them to deprotonate an intermediate at the end of a reaction. We've also seen that alcohols are weakly acidic. We've seen that they can react with more basic compounds to donate their proton. Something that we haven't seen is that the hydroxyl group can actually be turned into a better leaving group. We've only seen that through protonation so far, but hydroxyl groups can actually be turned into halides, and they can also be turned into some more interesting species. So let's recap acid-base reactions of alcohols. We're going to speed through this because you do already know this. So alcohols can be used as bases. They are Lewis bases because they can donate an electron pair, allowing them to pick up a proton. So if you put an alcohol in a strong acid, it is in fact going to pick up a proton. It's going to break the bond between the proton and the future conjugate base. And then you end up here with a positive charge on oxygen and your conjugate base. Usually we do this because we're trying to create a good leaving group. You can also use alcohols as acids. If you add in something that is more basic than an alcohol, or even if you want to just talk about the equilibrium of alcohols and water, you can form an alkoxide, and in this case hydronium. Now note the equilibrium arrows are showing that we favored this, right? We're not going to be able to create an alkoxide and hydronium at the same time, but I guess it's kind of fun to think about. But if you had a much stronger base such as azonide, we could definitely make this happen. Now let's talk about something really cool. So you can convert alcohols into alkyl halides. We're going to bring in some new reagents here, although not in this first step. I spoke a little too soon. So first of all, you can do this through an SN1 reaction. This is something you've seen before. You can take a highly substituted alcohol, react it with a halogen acid, and swap it out for a tertiary alkyl halide. So remember, in this mechanism, the first step is that we pick up the proton, and then we form a protonated intermediate. The equivalent of water leaves as a leaving group, and then chloride comes in. This is an SN1 mechanism that we've looked at several times. You can also do this on a less substituted alcohol. You just need to add in some more stuff going on. So you're going to have to reflux this. A lot of times also, if you're performing this reaction, which I actually do in one of my courses, you're going to have to add in another much stronger acid, such as sulfuric acid. It can be done, but this is not necessarily the most efficient way to accomplish this, because you do have to reflux a strong acid in order to make that work. Reflux means boiling, but collecting the condensation and letting it come back down. So a better way to do this, even though the yield is a little lower, is to react an alcohol with PBr3, phosphorus tribromide. You do this at low temperature over 4 hours, and you end up displacing the alkoxyl group, or sorry, hydroxy group, got in ether mode, I guess, with the bromine. And then you have a little bit of a side product happening. You can also turn an alcohol into a chloride by reacting with thionyl chloride. That's what SOCl2 is. The structure of that is, I'm going to draw it off to the side over here, like so. And then pyridine is a base that you need in order to accomplish this reaction. Pyridine is a heterocyclic aromatic amine. Looks like this. I'm going to erase these and get them out of the way. And this is just going to swap out the hydroxyl group for a chlorine. So a really handy reaction. So again, you can react an alcohol with an acid halide to get an alkyl halide and water. The order of reactivity is equivalent to the order of reactivity for SN1 chemistry. If you do this with a tertiary or secondary alcohol, it will be SN1. If you do it with a primary alcohol, it's going to be SN2. You're going to create a good leaving group, and then the halide will come in and bump it out. As far as acid halides that this works with, hydriodic acid, hydrobromic, hydrochloric will work really well. Hydriodic is going to be the most reactive. It's also the most acidic. With HF, it's really unlikely to occur, so that's not a reaction you're going to see very often. Another thing that you see pretty regularly that we also were exposed to in the substitution chemistry chapter is that you add in acid and you add in a halogen salt. Now, one of the pros of doing this is that when you do this, you can actually add in a large amount of the halogen. And this is really good if you have a primary alcohol that you're trying to do this with, because you can protonate the alcohol with a very small amount of acid, even a catalytic amount, and then the halogen can be free to kick out the protonated alcohol. So this can be a much more effective way of accomplishing the same thing as adding in an excess of the halogen acid. You can also do this with a Lewis acid catalyst, such as zinc 2 chloride. This will work with a primary or secondary alcohol only. This is something you don't see very often, but it is another way to do this. Because again, trying to do this reaction for a primary alcohol with a halogen acid doesn't go super well. It does take a little force with heat, maybe with a stronger acid as a catalyst. Typically, just being able to add in more of the nucleophile is better, because remember, if you're going through an SN2 mechanism, the rate is equivalent to the rate constant times the concentration of your substrate, which is your alcohol, times the concentration of your nucleophile, which in this case is X minus. So if you can increase X minus, you're going to increase the rate of the reaction. Okay, there's one other topic in this video here, which are leaving group derivatives of alcohols. So we already know that alcohols are not particularly good leaving groups. We do a lot of things to change them. We can protonate them. We can now convert them into halogens. Those are effective ways to do that. There are also these compounds called tosylates, mesylates, and triflates, and these are also really good options. So I know this slide is kind of confusing looking. There's quite a bit of information here. So the tosyl group is the one on the left. These are all compounds that feature sulfonyl groups. So tosyl is actually short for toluene sulfonyl, and toluene is a benzene with a methyl group. But anyway, you can call it just the tosyl group. The shorthand is TS. And once it's been reacted with an alcohol, typically you're reacting tosyl chloride, so you'd have a chlorine here, with an alcohol, you end up creating what's called an alkyl tosylate. So then at this point, the alkyl group is more susceptible to nucleophilic attack, and then this is able to leave as one giant group. And then the resonance that this negatively charged oxygen will have with the rest of the species is what allows that to be so. We also have the mesyl groups. This is methyl sulfonyl. And then we have an alkyl mesylate, is the product of the reaction of mesyl chloride with an alcohol. And then we have the trifle group. This one, the name stands out a little bit. Trifle is short for trifluoromethane sulfonyl. So we have 3 fluorines on this carbon here. So this was methyl sulfonyl. If you add 3 fluorines, it becomes trifluoromethane sulfonyl. So yeah, I guess they just didn't want to go with an SYL ending because then it'd be like trifle. That was dumb. Sorry. Trifle group. Anyway, moving on. So you would react trifle chloride with an alcohol to make an alkyl triflate. All of these have several different shorthands. Tosyl is pretty much usually just TS. But the mesyl group, sometimes you see is MESO2, referencing this portion, or just MS. When it's the alkyl mesylate, you might see MESO3R or MSOR. The triple group is CF3SO2 or just TF. So you definitely want to be able to recognize these shorthands. And again, the groups themselves are on top of the line here, and the ones on the bottom are the alkyl derivatives. And you create these by reacting the alcohol with the chloride compounds of all of these. So tosyl chloride, mesyl chloride, and trifle chloride. So for example, if we react ethanol with mesyl chloride in the presence of pyridine, because you need something to deprotonate the alcohol once it's attached to the mesyl group, you end up with ethyl methane sulfonate, which is ethyl mesylate. You can do the same thing with the tosyl group. So this is what tosyl chloride looks like when it's drawn out instead of just written out as TSCl. You can react it with an alcohol. A primary alcohol typically is what you're using with pyridine, and you end up with ethyl p-toluene sulfonate or ethyl tosylate. Be really careful that you are familiar with these structures as they actually exist. A lot of students get in the habit of just always shorthanding TSCl, MSCl, and then when they actually do see the compound, they get thrown for a loop entirely. But then you say the word mesyl and they're like, oh, I know that. Well, no, you didn't. It's because I was right there and you didn't use it. So make sure that doesn't happen to you. So why do we do this? Again, they are good leaving groups. So if you have an alkyl sulfonate and you react with a nucleophile, whatever carbon is attached to the oxygen, and it's kind of weird that it says R here, the carbon that is attached to the oxygen is going to be a good electrophile, and then the oxygen as part of the whatever sulfonyl group you have going on there is going to be able to leave as a more stable leaving group in a way that hydroxide cannot. Because hydroxide is a strong base, but a sulfonate is not. So this is an SN2 reaction. And you get left over with a sulfonate ion. So I'm going to show you real fast the mechanism for tosylation or methylation or trifylation. So reacting an alcohol with, in this case, the mesyl group, mesyl chloride, the alcohol oxygen attacks the sulfur. You push the electrons from the double bond up onto the oxygen. And then you end up with this intermediate here. It looks a lot more complex than it actually is. Here is your original alcohol molecule. Here is the mesyl chloride. And what's happening now is the oxygen is going to reform its double bond and kick out the chlorine. And then the pyridine is going to come along and deprotonate that intermediate. And then you have your alkyl sulfonate or alkyl mesylate in this case.